For the kind introduction, and welcome everybody here and also virtually. So let's start with some introduction. So the project I'm working on is called DeepL, Deep Learning Applied to Animal Linguistics, and the overall goal is basically to decode animal communication, in particular here the killer whale as prototype species, using a hybrid approach between bioacoustics and machine learning. And when you want to decode animal communication, you have to fulfill basically two components. The first is identification of vocalization events and recurring acoustic patterns in the first step, in order to try to derive some semantic and syntactic structures, and afterwards mapping those acoustic patterns along with the associated situational behavior in order to decode communication. Obviously, this requires huge amounts of data. And one of the biggest and largest bioacoustic data archives recorded on killer whales is the Orchive. The Orchive was recorded via 6 stationary hydrophones and contains 20,000 hours of underwater recordings, starting from the recording started from 1985 till 2010, together with 30,000 handwritten lab book pages available in a PDF format. On the left picture here, you can see the OrcaLab, which basically collected this data set. It's a small research station located on Hansen Island, which is a tiny island around Vancouver Island. And on the right side, you can see the hydrophone network of the OrcaLab and the covered recording area. So, but not only existing data sets are important, we also conducted our own fieldwork expedition in 2017 and 2018. I brought the research trimaran Tomorrow along the coastal waters here of British Columbia. In 2017, around, I would say, the place of, more or less the place of Vancouver Island, and then up to Alaska in 2018. With this 15-meter research trimaran and custom-made high-sensitive and low, we used a custom-made high-sensitive and low noise tone array in order to collect additional 1,000 hours of audio recordings along with 90 hours of behavioral video footage. On the left picture, you can see the research trimaran, which is a drone picture, and on the right side, the expedition route. Okay, but now coming to the actual task. So we want to conduct killer whale call type identification. What is actually a killer whale call type? So killer whales produce 3 different types of sounds. Echolocation clicks, which are more or less pulsed calls, pulse-like structures. Whistles for close range interactions. And the most intensively studied and well-known vocalization pattern is the pulsed calls, or also named killer whale call types. These are distinct spectral patterns. I have visualized here some of the existing or well-known patterns. The problem with this vocal repertoire is that most of those killer whale call types were handmade. So those observations are all handmade and therefore also just based on a limited data set. And what we want to do now is we want to design a large-scale, data-driven and machine-based call type identification approach to gain totally new and much deeper insights into killer whale communication. Therefore, we basically try to identify, on the one hand, known call types, but we also want to try to identify, even within a specific type, are there differences? So on the one hand, a inter-call type variety, and on the other hand, a intra-call type variety. And in addition, we also want to identify potential unseen or unknown vocalization patterns, which enables which gives us then the chance to identify those acoustic patterns, recurring acoustic patterns, and try to map them to the respective behavioral footage. However, this is a very challenging scenario. We have massive unprocessed noise-heavy data volumes. We have a lack of sufficiently large and human-labeled and representative call type data, and we have actually also missing information about the intra and inter-call type variations. So we've used multiple task-specific machine learning approaches to prepare, enhance, and process the entire bioacoustic data material, basically. So now coming to our actual ORCA-SLANG pipeline. The ORCA-SLANG is a multi-stage, semi-supervised, deep learning-based call type recognition framework consisting of basically 4 components. The first component is a ORCA versus noise segmentation. So we took the tapes and tried to remove the background noise and extract the valuable ORCA vocalizations. In a next step, we took those machine segmented ORCA vocalizations and denoised them. So also removing the overlaying noise, not just the surrounding noise. In a next step, based on those denoised samples, we conducted a deep feature learning in order to derive bottleneck features for then the last step, semi-supervised call type identification, which includes basically spectral clustering as well as supervised call type classification. But now discuss each component. So the first step was ORCA noise segmentation. Therefore, we used ORCA-Spot. It's a previous work of us. ORCA-Spot is a ResNet 18-based convolutional neural network, which was trained on noise samples and ORCA samples in order to solve this binary classification problem. And with that network, we segmented all 20,000 hours in about 8 days, ending up with 2.5 million ORCA segments. And those 2.5 million ORCA segments were now used in a next step where we used also a previous work of us. It's called ORCA Clean. It's a deep denoising network based on the UNet architecture, and the network was trained via 2 different alternatives of spectral input and output pairs. So either an additive noise corrupted spectrogram compared to the original noisy spectrogram was fed into the network, or the original noisy spectrogram versus a binary mask, a machine-generated binary mask of that spectrogram. So in both cases, the original input was noisier than the output, and this allows us to denoise those ORCA vocalizations, and I have visualized here a couple of examples how it looks like. And we denoised all 2.5 million segments. And then in the next step, we applied also previous work of us. It's ORCA Feature. It's a ResNet 8, slightly modified ResNet 18 undercomplete autoencoder in order to learn robust bottleneck features as input for subsequent ORCA call type classification. And I also have visualized here the input, the denoised input spectrogram, and the reconstruction of the autoencoder, right? So finally, we have to conduct this semi-supervised call type identification. This is basically this step is subdivided into 5 sub-steps, whereas the step 1 to 4 were repeated 5 times. So the first step was we randomly selected a portion of 20,000 samples with a very high network confidence of our segmenter. Out of the 2.5 million machine segmented clips, we clustered them into 200 clusters. And afterwards, we verified those clusters with a supervised trained multi-class neural network which knows or which models 9 call types. But the problem of this actually supervised trained model is that we had only around 500 labeled samples for these 9 call types. So we verified the clusters, and each cluster which had a higher purity of 0.7, all of that cluster content was then assigned to this specific call type. So in the next step, we had the k nearest neighbor step. So all remaining 2.5 million samples were then assigned to those known call type clusters in order to compute somehow a data enlargement. And in the last step, or in the 4th step, another round of supervised classification was applied, but now to the entire to the clusters with much larger content in it in order to verify the cluster purity and actually the accuracy, right? So, and these 4 steps were computed 5 times. And in the 5th step, we calculated then the unique identifications of the known call types across all 5 trials, but we also did investigations into potential unseen sub-call types as well as unknown call patterns. So this is just a summary slide which shows again those 5 steps. So first spectral clustering, then a first round of supervised classification, a KNN-based assignment of all the remaining segments, again verifying those clusters with the supervised multi-class ResNet 18-based network, getting the actual cluster purity, and in a last step extracting all those unknown, known, and sub-call type patterns. So coming to the results, on the left you can see a table where you see 6 out of the 9 call types which the network was trained on. And while focusing on the second column now, after the KNN-based assignment, we had, across all 5 trials, we had 625,000 of those call types. Those 625,000 were then verified via this supervised trained model, achieving an accuracy of 90%. So 560,000 were classified correctly. And while then only considering across all 5 trials the unique samples, we ended up with 235,000 clips, fully automated, machine identified across all these 6 known call types. I have visualized here those 6 categories, each with 18 spectrogram examples, randomly chosen from the entire cluster content in order to give you an intuition about the cluster quality here. And in a second step, we also had a identification of unknown call type recognition patterns and sub-call type patterns. I visualized here just an example. So on the left side, this is an unknown, basically a call type which was not modeled in this supervised trained network. And as you can see here, this call type also shows a very large intra call type variety. And due to the fact that we were not able to say what that might be, we took, according to the tapes where we recognized this call type, we took the handwritten lab books and had a look at it, what the biologists documented there. And actually it was quite, it was quite good that we were able to have this like this name here, transients. So this is actually a different population within the coastal areas of the northeastern Pacific. And we were able to identify it with that approach. And on the right side, I have the intra-call type variety. So we took all the 140,000 previously machine identified unique N4 calls and just clustered them. And spectral examples of different potential sub-call alternatives, each of them part of the distinct clusters, are visualized here. So here you can also see a large intra-call type variety, even within this specific category. Okay, finally coming to the conclusion and some future work. So in this work we present ORCA-SLANG, which is a multi-stage deep learning framework unifying ORCA noise segmentation, denoising, feature learning, and also a final semi-supervised call type identification approach. We were able to recognize known but also unknown killer whale call types within a really huge database which contains actually more than 20,000 hours of underwater recordings. This enables for the biologists totally new insights into population, group, and individual related acoustics analysis. And some future work, what we want to do, we want to use those known and unknown call type findings to identify those recurring patterns, which we then can map to those behavioral video footage which we have from our fieldwork trips. And in addition, similar to Animal Spot, which is also work of us, it's an animal-independent segmentation network and also Animal Clean, an animal-independent denoising network. We want to try to bring ORCA-SLANG also as an animal-independent system. So, thank you for your attention, and I hope I will see you all at the student party afterwards, and thank you for your attention, and I feel free to ask questions now.
All right, such a fun topic, so there must be many questions from the audience. Yeah, please, if you have a question, please go to the chair over there and take the microphone.
Yeah, way over there.
This is required for the people at home or following remotely.
So, hello, Andreas, Maier, my name, and I would like, did you know that there is so much transient data in there, and were the transients actually part of the call catalog, or were they only done for resident?
The call type catalog was only includes calls from this resident population, and actually nothing from those transients. And we were able to discover those calls across several tapes in the year 2000. And then once we looked at those lab book notes, actually exactly at those days, the biologists wrote there, okay, transients swimming by, because this is actually not, I would say, super common that they swim in those regions.
That's a very cool result, isn't it?
Yeah, I think so. I hope so.
More questions? Yeah, I have a question.
Yeah.
So, also in your future work, but also in your current work, you're trying to relate the calls to semantics, right? So,
I mean, the goal is first to identify hopefully the entire variety of those vocalization types, like for human speech, for example, words, phonemes, or so, and then we can have a look at recurring patterns. Yeah. And once we know, okay, we observed 1,000 or 1 million times this pattern, we can have a look at what happens there, what kind of behavior they show.
Right. So, but to relate that, you have the notebooks from the biologists.
I don't think this is sufficient.
Well, that's exactly where my question was.
Yeah,
going.
yeah, right. This is exactly why we did this fieldwork, our own fieldwork expedition. There, basically the biologists were on the boat filming the animal, or recording the animals, and describing their behavior while the sound was recorded with this towed hydrophone array behind the boat.
Yeah.
In order to bring it somehow together, right?
Yeah, because, for instance, the relative positions of the animals must be very important.
Exactly. So localization is also a big topic here.
Yeah. Yeah. And then a more detailed question about the noise removal. So first you do what in speech we would call voice activity detection, right?
Right.
So,
you can consider it.
But you then throw away the surrounding what comes before it or comes after it, but that could actually be useful for noise reduction, right?
I mean, those 20,000 hours, they were passively recorded. So I would say 90% of the data set is just noise, or probably more. So in the first step, we try to get rid of those things. And afterwards, once we trained this denoising system, because still when you have this call type, there is still overlaying underwater noise on this call type. Yeah. And we tried this approach without the denoising, and it kind of messes up the clustering, right? The high dimensional feature space was not that.
But I mean, to remove that noise, you can, from the examples that you gave, you kind of look at only the call itself.
Yeah.
But not what comes before it and after it. And I mean, just like if you would do simple spectral subtraction, making an average of the spectral characteristics, measuring the spectral characteristics
Yeah,
before and after the call.
we tried it, but we have 20,000 hours with a huge, I mean, noise variety in,
Yeah.
and this works, for example, in the year 1985, where you have not that much boat noise, like in 2010, where you have the fishing industry, touristic boat ships passing by, and then this doesn't work anymore. Yeah.
All right. Yeah, I think we have last check if no online questions. And
Okay, thank you.
thank you very much.
Thank you.